Hi, everyone. Thank you for joining us today for this webinar covering all things Ceph. My name is Lauren Grobe, and I am the head of marketing for OSNEXUS. I'll be your host for today. To start things off, we are going to do a Q&A with our panelists, and we have some really great guests, so I am going to introduce them right now. First, we have Anthony Diatri. Anthony has been deploying and maintaining large-scale Ceph clusters for service providers since the early days of Ceph. He's a top Ceph expert and author of multiple books, including Learning Ceph and Ceph, Designing and Implementing Scalable Storage Systems. Next, we have Paul Dardo. Paul has been a software engineer for over 20 years and works heavily with Ceph. Paul has developed multiple Ceph architecture guides for deployment of Ceph on Dell systems and has been a speaker for OpenStack conferences on Ceph. And last, we have Steven Umbihocker, OSNEXUS's founder and CEO. Steve is a longtime enterprise storage industry veteran, having worked in this space for over 20 years, and he holds over 20 patents in storage technologies. Thank you to our panelists and all the attendees for joining us today. So we are going to jump right into the panel discussion, and we will take attendee questions at the end of the discussion. And then we'll wrap up with the demo from Steve on the OSNEXUS solution design tools for Ceph. So with that, Steve is going to kick us off with our first panel question.
All right. Thanks, Lauren. We're going to really, with the panel discussion, we really want to educate folks about as much as we can about how to design great Ceph clusters. And so we're going to be looking at kind of a couple of primary use cases. One is more of a performance type use case, and one is more of like an archive and backup type use case, and the differences between the two. And we're going to talk a bit about scaling the different aspects of the storage servers from a hardware perspective, but we're also going to talk a little bit about the services like the monitors and how to size and scale those, and talk about different erasure coding levels and optimal erasure coding levels, and learn a bit more about how these large clusters are maintained. Anthony's experience there, we'll be hearing some stories from the field there, and then a little bit about some of the new things coming with Ceph Octopus and new areas of innovation with Ceph. So to kind of kick it off, we'll talk a little bit about just sort of the Ceph monitors. We're kind of assuming that the audience knows a bit about Ceph, that it's a scale-out file block and object store, and one of the key components in the Ceph, or one of the key components is this component called the Ceph Monitor, and you have to have a quorum of these running in order for your cluster to be active. If you lose a quorum of monitors, then it goes, the cluster will stop. And so the availability of the storage is no longer there. But Anthony, can you tell us a little bit about kind of like what your recommendation is between like the monitor count?
Sure. And the absolute rule of thumb is that you want an odd number, because you don't ever want a split brain situation. People who are used to clustering or databases will recognize split brain, where, I mean, say you have four monitors and you have a network split between them. So you have two mons over here and two over here. Who's in charge? And you don't want them both thinking that they're in charge, and because then how do you reconcile? And so you always want an odd number. And so, you know, one has certain reliability limits. 3 is a good number for, you know, a small cluster or something in a lab for development, something like that. With 3 monitors, you can tolerate the loss of one node if it crashes, if the hardware smokes, if somebody brushes the power, you know, with their elbow as they're walking down the DC, or even for maintenance, if you need to replace RAM, if you need to, or doing Ceph upgrades, you can tolerate 1. For, you know, real production, I suggest 5 so that you can tolerate 2 failures.
Yeah.
Any more than 5 is overkill, I think, for almost all applications.
Awesome. And what about like things where what do you guys see in terms of load on the monitor nodes? And do you generally separate the monitor nodes out, or do you prefer running them on the same boxes? Maybe, oh, go ahead, Anthony. Yeah.
No, if Paul has something to say, go ahead.
So my experience is not in production. So the work that I do at Dell EMC is within the lab environment. So we could do a lot of things and not have the dire consequences one might have in production. But on the ready architectures that we published last year, we decided to go with a 4-node minimum size. And for that 4-node minimum size, we had co-located daemons with the various daemons containerized. And it worked just fine. But Anthony brings up a very good point that availability is paramount importance when it's production.
Yeah, and having the 5 monitors really keeps you can have 2 nodes off. Yeah, I wholeheartedly agree.
Which I've experienced.
Right. Yeah. And
by and I favor having them as separate nodes, and they don't need to be very big nodes at all. One use single socket, twin system, something like that, blades even.
Okay.
So that you separate their maintenance from the OSD maintenance.
Right. It just gives you especially with larger clusters, right? Having the services running on separate boxes gives you just that much more flexibility as you go into the maintenance cycle, right? So
yeah, now certainly, back in, say the Firefly days or Dumpling, capacity was an issue. But with the changes that have happened in subsequent releases, especially with some of the work that Dan at CERN did with a very large cluster of 10,000 OSDs, the MONs scale a lot better. And so now the number of nodes itself really isn't a factor, I think, in the MON count. It's more about, the space that you have and how concerned you are about availability.
Right. And the monitor nodes are the ones that you're upgrading first, right? Because then they've got the backward compatibility
Usually,
with
yes.
older OSDs. Yeah. Yeah. That's really great. Another question. Let's talk a little bit about the front end and back end networks that we've seen more and more clusters being deployed with single networks, and wanted to get your guys' input on that. What's your thoughts on kind of having a front end versus back end separate 2 networks for your Ceph clusters, or versus having one? Are there some benefits to the 2? Go ahead, yeah, Anthony. Yeah, go ahead and start that one off.
I don't want to monopolize.
Oh, that's okay. Or Paul? Yeah,
I'm interested to hear Paul's thoughts too.
So I guess my thinking is if you have relatively lower bandwidth network, so if you've got a 10 gig network and or heaven forbid a 1 gig network, I would suggest 2. That would be what I would be more comfortable with. But if you're at a 50 gig network or 100 gig network, then I think 1 is just fine.
I would agree. I actually currently have legacy OSD nodes that are on gigabit connections. And
wow. Okay.
But we're replacing all of those clusters.
Yeah.
Actively doing that. Yeah, certainly, I think that was really good guidance, that came from a day when people were mostly running gigabit networks. And with today's modern networking, I think it's not nearly as true as it used to be. The idea has been to kind of separate replication traffic from traffic among the monitor nodes and between the cluster to clients, so that if you have heavy replication traffic, if you're adding a bunch of capacity, if you had a node or 3 fail, then that traffic would not kind of overwhelm and block out the traffic to the MONs that's critical for the cluster to operate, or for the clients, because everything is about client impact, and everything we design is to keep the clients from being impacted. And Ceph lets us do that. We just have to make the right choices. But again, with modern 2500 gig networking, I mean, you can still have a single link and do VLANs with QoS or something if that's a concern for you. But increasingly, the simplicity and the switch cost and the cross connect cost, et cetera, of having a single network is appealing.
Yeah.
That also saves you from a couple of weird states. I won't go into the details, but from some hard to debug kind of flapping states.
Nice. And so I guess the other nice benefit too is you go with the faster networking, you've got lower latency, and you can build nodes that have faster storage in them as well, right?
Yeah, I've read that actually 25 gig networking has lower latency than 40, but don't take that as canon. That's just something that I've. And so, I recently talked to somebody who was starting off with Ceph, and they were planning on 2 NICs per machine, and they're going to have one for a public network and one for replication. And I advised them, you do that, you don't have redundancy, you lose a connection, you can't take your switches down, for availability. You're better off if you only have those 2 of doing equal cost routing or bonding, so that you can exploit them for redundancy, because you don't really need to separate that traffic in a lot of cases.
Yeah, that makes perfect sense. And Paul, did you use a single network when you were doing a lot of the performance testing there for that database performance testing project?
We used 2 networks.
Okay, and were those 25 gig?
Yeah, they were each bonded.
Okay.
Dual active paths.
Okay, so in that case, you guys separated it out.
Yeah.
Yeah. Yeah, I really like that that kind of trend towards the single network, like you're saying, Anthony, kind of eliminating some of these potential cases where you have one half of the network out and not the other, and flapping kinds of things, and just sort of the overall cost savings and simplicity. Let's see. One of the things that was I was really, I think that there's a lot of lore out there on Ceph and sizing the data devices, or the amount of RAM per data device. And I think that would be a great thing to talk about next, is how much RAM should you have per data device that you go and add to the cluster. And for those unfamiliar with the Ceph terminology, there's a thing called an object storage daemon. There's that's kind of a one-to-one mapping to the data device. You might also have that accelerated with some caching tech or components. But just in general, Paul and Anthony, maybe Paul, start this one off. How much? What do you do? What did you do in terms of sizing some of your different performance configs as a RAM to capacity ratio?
Well, what we've looked at and what we found is that going up too high doesn't necessarily help you a whole lot, because Ceph tends to be sort of CPU intensive. What we go for, and what's worked best for us in our experience, is to have the sweet spot seems to be 192 gigs of RAM. So when using the Intel processors, it's got 6 memory channels, and setting it up to where you've got 12 16 gig DIMMs, 6 paired up with each of the CPUs seems to be a sweet spot. You get by having all memory channels of the CPU populated. That's where you get your best memory access. So that's really kind of the biggest deciding factor for us in deciding on the 192 with the 12 by 16.
Yeah.
But I guess one could argue that this is more in the olden days of having file store. Having more memory could be used for file system cache, but now with Blue Store, I don't think it seems to be as important. And so I think I still run across a lot of people that specify they want 384 gigs of RAM, but we haven't seen any objective studies in our labs where that seems to be beneficial.
That makes sense. Yeah. And Anthony, does that kind of match with your thinking too? Like 192 is a generally good number?
In context, I think it depends on a bunch of factors. One of which is, the size and capacity of the node, but also the use case. So, if you have, a node that only has, 3 1 terabyte OSDs on it, you don't need a lot. And in use cases like, just archival storage, for example, or in small clusters, you don't need as much. There used to be a rule of thumb of 1 gigabyte per every terabyte of OSD space, and I think that was more because there needed to be some rule rather than a lot of technical behind it. And certainly that was in the file store days when everything was XFS and relying on the page cache. As Paul mentioned, with BlueStore these days, and almost certainly any new deployment is going to use the BlueStore backend today. There is a memory target built into BlueStore, and you can change that target around. Sometimes it will use more than that under heavy duress, but it really helps avoid kind of the runaway that we used to have to deal with. And so, the default memory target for BlueStore these days is 4 gigabytes. And so I like to, on say a block storage cluster, I like to provision enough memory for each of them to have 8 because they will exceed that target sometimes. And so it's more of an OSD count versus capacity.
Right. So
and in larger clusters, you have more placement groups that take up a bit more memory as well.
Yeah, that makes sense. So if you have like 20 all flash OSDs and you did the 8 gigabyte per, then that would be a good example of like a 192 type.
192.
Config. Yeah.
Exactly. And
Yeah.
when I was deploying, 24 SATA SSD drive storage systems for block storage, 192 was what we settled on, and it worked really well. And that included enough headroom for when things get tough, which is what guidance doesn't always tell you, is that you can have enough memory to run steady state, but it may be not enough, when something fails, or if you expand the cluster. And I've definitely experienced those scenarios.
Nice. Yeah. And it's kind of, when it goes into that rebuild state, it's sort of like the whole cluster needs more RAM to be able to start putting more of that metadata and such into RAM to start rebuilding that device.
And if you don't have it, then you can end up with a cascading failure. I've been there.
Okay. So yeah, don't under design these configs where you don't have the RAM. Otherwise, you could be in a situation where you got to go into the box and manually force the cache to be smaller so that there's some more room for these OSDs to build out and repair.
Or you have to restart them every 5 minutes and let them do a little bit of work before they blow up.
Sure.
But as Paul says, with every CPU, or motherboard server architecture, there are memory population rules that make sense.
Yeah.
So if you have a 2-socket system, you want the same amount on both sides. Depending on your memory channel, you may want groups of 3 or 4 or more or whatever, modules that kind of inform the memory sizes that make sense for a node. And so sometimes we end up rounding up, just for those. I've actually seen one node that was a 2-socket server that had 4 DIMM slots on one socket and 8 on the other.
Whoa! So it's totally asymmetrical.
That I was stunned. I thought I was mistaken.
Okay.
But that was Kurt has a pending question there about dense systems. That was a dense system that had like 90. It was like a 4U system that had 90 drives in it, and so that was kind of a limiting factor.
Okay. Yeah. I think when you go with those really dense nodes, I think that that's a key thing to keep in mind too, is that you've got to scale everything else with it, the RAM, the CPU, the network, and all of that. Otherwise, you're going to have a bottleneck at one or more of those spots. And I think that's kind of a good segue into sizing CPU. So, um, yeah, in terms of like, what are your guys' thoughts on sizing CPU for like an archive use case versus um, a performance use case where you're really after maximum IOPS and all that? And here we'll pass the baton back to Paul.
Yeah, so I think in the context of like an archival use case, I think probably something in line with, let's say, like a Silver family of Intel processors, probably 12 cores, thereabouts, is just fine. And if you take the opposite extreme, where performance is everything and you're willing to pay for it, if you've got like all NVMe, our studies showed that 7 CPU cores per NVMe provided the best overall throughput. But once you start doing the math of 7 cores per device, you don't get too many devices in there before you start running out of CPU cores. Fortunately, one of the good things is that Intel made available a 28-core CPU down into the Gold family that used to not be there. It's a 6258R, if I'm not mistaken. But anyway, in the case of like all NVMe maximum performance, I think that's the overriding concern, is to have enough sufficient cores per device. But the flip side is like in the archival case, something like a 12-core CPU, I think is just fine.
That's really great. And did you, with those performance configurations, did you pin the CPUs or the OSD to specific CPUs, or just start the OSDs and kind of let the operating system sort it out?
We evaluated pinning them with the pinning and without, and we found that it wasn't really we didn't notice a benefit of having it pinned.
Yeah.
But what we did do is we spent a lot of time making sure that things were balanced across the 2 different CPUs. So we had, equal number of drives, NICs, and balance things out as much as possible so that we wouldn't have one of the processors overloaded and the other one underloaded.
Okay.
Yeah, I've definitely seen measurable performance improvements by distributing interrupts for NICs and HBAs across cores in cases where without that one core may get all of the interrupts.
That makes sense. Yeah, so kind of it sounds like, especially on these really fast configurations, the kind of like 7 CPU cores, if you're doing a lot of NVMe, that'll keep it so that you're not fully saturating your CPUs when you're under heavy load.
Now, Paul, did you see diminishing returns as you started approaching 7 cores?
Yeah, we tested both below 7 and above 7, of course. But the way we started out with 12 drives in the server, and we were pretty sure that was too many, or too few cores per device. And so what we did is we started dropping it down, and then run our set of tests, do the calculations, find out what we're getting per CPU. And we went from 12 down to 6, and we found that at each increment of 2, having 8 in our particular case with our configuration provided the best results.
Okay. Nice. Yeah, and that's great that they've got that, like you said, the 28 core processor available. Was that in the latest 3rd gen scalable processor?
I don't know offhand like what I tend to think in the like Cascade Lake. I don't really
Oh yeah,
offhand know what that
Oh yeah.
corresponds to, like in the marketing.
Oh, it's the second digit. So you said it was a 6258, I think.
6258R.
Yeah. So it was a
It
second
came out
gen.
at the end of February, if I'm not mistaken, of this year.
Okay. Very cool. All right. Let's talk a little bit next about erasure coding, kind of when to use it, when not to use it, and a little bit about scaling the configuration for erasure coding. For those that are less familiar with erasure coding, basically it's a way of striping the data across the cluster so that you've got fault tolerance and high availability, and it does so by having these coding blocks. So you've got some number of data blocks and some number of coding blocks. So you might have 6 data blocks and 2 coding blocks, and then that combination of 6 plus 2 is 8. So you need a minimum of 8 servers. And for each coding block that you have, in that example, 6 plus 2, you can have 2 servers offline, and the data is still available. So let's dive into that a little bit more and talk a little bit about, because you're striping across the servers, what are kind of the use cases where erasure coding does really well, and where is it better to use more of a replica style? And replica style in Ceph is a little bit more like RAID 10 for those that are familiar. It's more of a mirroring technique, and so it's got similar counterpoints to like parity-based RAID is more akin to erasure coding versus replica is more akin to RAID 10. And yeah, Anthony, why don't you kick that one off?
Sure. The most common reason why people consider erasure coding is to get more usable storage out of the raw storage. Say you use a traditional 3-way replica system, and you have 3 petabytes of raw storage. You have more or less 1 petabyte of usable storage. Where with an erasure coding profile, you could have 2 or even more usable storage. There are trade-offs with you have to carefully design your cluster around the number of nodes, the number of racks, so that you don't end up in a situation with erasure coding, especially where if you take a node down, data becomes unavailable. Erasure coding also can present more of a increased write amplification, where especially if you're going on spinning hard drives, because you're sharding more, you're doing more operations to the drives. And so, in an archival or, backup, nearline, those kinds of situations, erasure coding can work, very well. With very fast devices, you may even be able to use erasure coding for, doing something like a flash pool serving block data to VMs or something like that, because the underlying storage has enough capacity and is fast enough.
Yeah.
And so really it's about, in most cases, it's about the capacity. The cost of the hardware and what you get out of it. It's really suited for middle to larger clusters. If you have a very small cluster with say 3 nodes, erasure coding can be problematic. But once you start getting up into larger clusters, then you have the ability to exploit the benefits of erasure coding more safely.
Yeah. And are there some erasure coding levels that are kind of the recommended go-to sizes for best performance in terms of K plus M?
I've read an article that suggests that there's some advantage to choosing K and M that have small prime factors. So for example, something like 7 might not be a good choice, but even numbers would be.
Yeah, that's our go-to as well. Kind of something where the K, the data portion's a power of 2, and then the M could be 1, 2, or 3, but basically kind of keeping within a power of 2 makes it so that the underlying data block of 4 meg can easily divide up across the stripe.
And there are actually some current on the user list. There are some current issues with overwrites on erasure coding, where you can actually have kind of stranded or abandoned space. But those things are improving. If you're writing a whole lot, if you're using, say, Rados Gateway and you're writing a whole lot of really small objects, it's very possible that you can have a significant 50% even of wasted space. But if you're writing large objects, then that's not an issue for you.
Yeah.
And usually, for real work, usually the values of M that people choose usually end up being 2 or 3.
Okay. Yeah, and the M, the coding blocks, that having 2 or 3 makes it so that you can have 2 or 3 systems offline at once, and so that's kind of also important from a ease of maintenance perspective and all that. And when Anthony's saying bigger objects, it's kind of the standard object size in Ceph is 4 meg, and so when you're talking something that's 1,000th of that, like a 1 kilobyte file or whatever, that's where it's better to kind of go with a replica style for your object store versus erasure coding. But if you've got sizable, multi-megabyte, gigabyte, terabyte files, then you'll be able to get those benefits. But
Absolutely.
those really small ones. And Paul, did you want to add anything in there on kind of like with regard to all of your database work? You were kind of avoiding erasure coding and going more with replicas, right?
Yeah. So I guess my thinking is all other things being equal, that default choice for block storage is replicate.
Yeah.
And default choice for object storage is erasure coding.
Yeah.
And it's conceivable that there are edge cases where even within those parameters, one might be preferable to the other. But I think it's kind of a safe default.
That's certainly a good rule of thumb. But even with object, you're in some of your metadata pools, your index pools, you want to still replicate. But certainly for bucket data, erasure coding is very popular for object storage.
Yeah.
And part of that is that with object storage, the use case really informs so many of these decisions.
Right.
With object storage, the users usually are relatively tolerant of latency for their operations, but they want a lot of throughput. Where with block storage, what I've seen is that by and large, the users, the biggest thing they care about is write latency. And so when implementing block clusters, say for, virtualization or OpenStack Cinder or anything like that, I've aimed at an average write latency of less than or equal to 5 milliseconds. And that's harder to do with erasure coding than it is with replication.
And for the media type, I think it just in general, you always want to be using flash storage nowadays. I mean, the cost of flash has come down. So for those anything that's like an RBD, that the block storage, you guys are generally seeing that all new deployments are replica and flash, right?
For something like providing database to VMs or something, sure.
Yeah.
But I mean, there are also archival use cases that happen to use RBD. My current employer has one where we have VM backup images or deployment images that are most of them never get read, and they're only written once. And the writing is asynchronous from the actual users, and so the latency doesn't really matter for them. And so we're using hard drives for those, for the economics, because it's actually something we don't charge them for in some cases. But absolutely in a case where somebody's trying to run a database or doing something that, especially with a low queue depth workload, it's very hard to fulfill that with spinning hard drives. You can do a thing where you put metadata, OSD metadata on a larger drive, and depending on your workload, that can help a lot. But it's certainly simpler if you can swing all flash.
Right.
And with some of the modern hardware that's available, that's increasingly cost effective compared to some hard drive systems. But I don't want to go down. I don't want to monopolize the call and go down.
No, that's really great. I think we should talk just a little bit more about how Ceph uses the write-ahead log, sort of an external write-ahead log and a separate metadata offload. And that's something that we kind of recommend in all platter-based configurations. And just because, a little bit more there on Ceph, but maybe you guys could talk a little bit about how all the writes complete beforehand, and maybe a little bit about that write-ahead log and kind of the importance of having it take some of the load off of the platter. Yeah, Paul, why don't you kick that one off?
Sure. So what we recommend is, so in the case of using spinning platters for the data, we recommend either SSDs or NVMEs. So in the case of SSDs, we recommend a 4-to-1 ratio, so 4 HDDs per SAS SSD, or in the case of NVMEs, depending on your workload, it can be like 12, 15, 8. It just kind of depends, but and on the other angle is if you're storing your data on, let's say, like SATA SSDs, we recommend a 4-to-1 ratio of NVMEs, so 4 SATA SSDs per NVMe, where your write-ahead logs are on the NVMe device.
So you're offloading, and that's a kind of a real, isn't that, it's such an interesting thing. It's sort of like there's these layers where you can go from PMEM, where you've got persistent RAM that's just wicked fast. I mean, that's the rocket fuel. And then you've got sort of the next tier of rocket fuel there with the Optane. And then you go down to NVMe, and it's kind of like you can make use of those log devices to even accelerate lower cost SSD, right? So that's I think that was part of what. Could you maybe speak to a little bit of some of the performance gains of kind of doing that tiering in some of your research there, Paul?
One of the things that I don't have is, unfortunately, I didn't do any of the tests of if you take those faster tiers out to see what kind of the delta is between those.
Yeah,
I don't have it. That would actually be an interesting question to see. But for performance sensitive things, we would always recommend going with a faster tier for the write-ahead logs.
Yeah,
assuming you have the slots for it and the budget for it.
Right. It seems like that would, from reading some of, I was reading one of your research slide decks last week, and it looked like adding some Optane in there really kind of smoothed out the latency spikes in some of those for some of those database workloads.
Yep.
Yeah. Cool. And then, Anthony, maybe you could speak to a little bit about like, the write-ahead log versus the metadata offload, and kind of how important is kind of one versus the other, or in general, everybody should be using both, or what are your thoughts on WAL and MDB?
You can actually split them so that you have 3 devices where the WAL and the DB are on different devices, but that's very rarely done. In most cases, you keep the WAL and the DB together. And as with so many things, a lot of it depends on your use case, because putting it on flash, especially accelerates your writes, less so with reads. And in some use cases, if you're putting your data on SATA SSDs, then you may not need an external device. But there are cases where, with SATA SSDs for the bulk storage, where you can gain, some increased, latency improvements by putting the metadata on something like an Optane, which is even faster.
Yeah, and the metadata is really there to boost the read performance, right? Because it doesn't have to then go to the platter to go do that metadata lookup right?
My thoughts are that it's more of an issue with writes and during things like cluster rebalancing.
Right. Yeah, because it's the same kind of thing where instead of having to write the metadata to platter, you're getting a gain on both the reads and the writes because it's got to go and shuffle all that metadata around, which is a lot of random I/O type pattern, right?
Mm-hmm.
Yeah.
But in general, reads are less expensive than writes. I think you often get less of a performance bump with reads than you do with writes.
Okay.
And with writes, by using the wall, if you have like a bunch of small writes, you can get some benefits by coalescing them into fewer operations that actually go to media. So, and that's very workload sensitive, but there are cases where that coalescing can result in a measurable improvement in the actual writes that go to the media.
Right. Yeah, because now it can do like a full stripe write or like a larger block write to the platter versus a lot of small writes.
And when you do any write to a flash medium, it has to erase a larger, they call it an erase block or a PE block or something like that. And so there can be a write amplification factor in there that if you have really badly misaligned blocks, you can actually wear your flash out really quickly. But most of the time, one doesn't have to worry about that.
Right.
But when a client writes data to Ceph, it will write it to whether you're using replication or EC, it will write it to one place, one OSD, which then farms out the replication to others. And the write doesn't return to the user until enough of those copies have been persisted to disk. And so by if we're using a slow medium like a hard drive, by putting those smaller, faster adjunct devices in there, Ceph is able to write to those and return more immediately to the user, and then it will flush those to the slower storage asynchronously.
Yeah.
And that's where we get the real benefits for write performance.
Yeah. I think that write ahead log is so critical when you've got the slow hard disk drives in there, so that you do get that performance and like Anthony's saying, the write Ceph's architecture is really great in that it ensures that the write has completed and it's on stable media before it goes back to that end user. But that also means that you've got to wait for that data to actually hit the platters, or with the write ahead log, you get this extra boost, because as soon as it hits the flash device for the write ahead log, that it immediately returns, like he's saying. And I think one other kind of thing on that, as I think that people should really take into account that they need to buy enough flash devices to mirror them, and to make sure that their journals, and especially like metadata, is mirrored. And maybe Anthony, do you want to talk to that a little bit? I mean, obviously, if you've lost the metadata device, if it's only on a single disk, then that could have a pretty big impact on the node, right?
Yes, and that's one of the big considerations when using external metadata devices. Back in the order of releases, we call them journals. If you have 4, 5, 10, 12 OSDs, each using a single device, think about what happens when that device fails.
Yeah. all those OSDs now need to completely rebuild.
At the very least, they go down.
Yeah.
I've seen some theoretical discussions about resuscitating them, but you're still going to have some data that didn't make it to them, and that's not something that 99% of us would ever want to try doing.
Right.
And so, and that's also the same with somebody asked a question about scaling that we didn't really get to. Part of it is figuring out what you can stand to lose, and if you have 10 OSDs on all sharing one drive, that's just single point of failure. If you co-locate them, then each drive is its own failure domain, and so you have to account for that when designing your cluster. And so if you mirror those partitions that get used for wall and DB metadata, let's call them, then you can lose one of those without having the much larger blast radius. The downside is that where instead of if you put like half of them onto one and half on the other, you reduce that blast radius, but it's still there. Where if you mirror them, or I've even seen people trying to do like RAID on a RAID volume that they carve out the metadata from, but I wouldn't advise that. Where if you mirror them, then in most cases you're not going to lose the OSDs when you lose a device if you repair it quickly enough. But it also means you're doing double writes and you're going to wear your media out a little, twice as fast. And so, you have to be sure that you pick good flash devices that don't have performance cliffing, but especially have enough durability.
Yeah.
And in most cases, you don't need really huge flash devices for this. And so it's more important to have durability than for it to be larger. And you can make it larger and get durability that way, but mirroring, definitely has some appeal in that way.
Those Optane devices have a ton of appeal for that use case then, because they've got such great durability. It's just the cost of them, right? That they're super kind of premium, but the smaller ones used as just a pure wall device is a kind of a fairly low cost way to get a lot of endurance and low latency.
And in most cases, you want to aim at around 60 gigabytes of space on that fast metadata device per OSD.
Yeah.
With the current code, there are only certain values, because of where RocksDB levels are done, only certain values that really get used. And so, for example, say if you allocate 200 gigabytes to each, then with the current Ceph code, that doesn't get you a whole lot more benefit than 60. If you went up to 300, it would, but few people have that kind of money. And so, throwing in a 16 terabyte, device for this purpose is overkill. You can get away with a much smaller device. With things like Optane, you're often limited by just having enough PCI slots.
Right. Yeah. So kind of summarize that. What Anthony's kind of saying there is, like, if you've got a box with that you're putting the SSD in there to accelerate, make sure that you add them in pairs so you can mirror it. Make sure that it's a good high endurance device, and think about 60 gigabytes of mirrored capacity for each OSD, for each platter that you add. So if you add 20 hard drives in there, take that 20 times 60 gigabytes, you're going to need somewhere around 1.2 terabytes of flash in that box. And you really, kind of to what Paul was saying earlier, you kind of, instead of just adding like two 1.92s in the box, it's better to add more pairs so that you can get more performance out of it. So if you have 20 devices, it's better to have two NVMe mirrored pairs, put 4 NVMe devices in there than one single pair, because it's gonna, again, it's like it's lending its performance to those 20 hard drives. Paul, does that and Anthony, does that kind of match up with how you guys would summarize it?
Yes.
Awesome. We are down to just 9 minutes left. So I was going to kind of give a quick demo of our design utility and then take some questions as well. Lauren, do you have some questions from the panelists? Maybe you could, why don't we do those first, and then time permitting, I'll jump to the design utility.
Sounds good, Steve. Looks like we have one question from DK. So thanks, DK. We have, the talk of balancing distribution of memory DIMMs made me wonder, is Ceph NUMA aware?
And Paul, could you talk to that one? You were talking about how you didn't really pin the individual processes. I don't think that Ceph out of the box is NUMA, where you've got to do the work to pin it, right?
Correct. To my knowledge, it's not, although Ceph always has new and exciting things going in. So it's possible it could be, and I'm just not aware that it is, but to my knowledge, it's not.
I think there may be some people working on that, but it's certainly not something that's available out of the box today. And I certainly have seen cases, rare, but I've seen cases where the memory on a 2-socket system where the memory was not being used in a balanced way. And pinning gets real complex. I've seen some very in-depth presentations where people were using like a 4-socket system, and they were pinning multiple NICs, multiple HBAs, and they were effectively kind of partitioning this expensive 4-socket server with expensive 4-socket CPUs, and effectively carving it into 4 1-socket systems. And at a certain point, there are all kinds of things you can do with Ceph. I really favor simplicity. The old KISS rule. And at that point, why not just have 4 1-socket systems? And depending on your use case, there are you can have systems that only have one NUMA domain. Like, for example, with AMD's 2nd generation EPYC Rome processors, you can run them with only one NUMA domain, so that's not even an issue. And they have lots of PCI bandwidth. Or there are people making ARM servers, that are really attractive, for certain use cases. So a lot of it just comes down to what you're trying to accomplish, and how many resources you want to put into trying to tweak the architecture to get the last 20% out versus all of the other things you have to do.
Right. Yeah. And that seems to be a more increasingly more popular thing, is that, like you're saying, that AMD EPYC, certain use cases, giving you more PCI lanes for NVMe devices and all that. It kind of provides some more competition out there in the market space. It makes even the Intel stuff a little bit more economical as well, no matter which, whether you're going to AMD or the other. But yeah, I think that's a really good point. Kind of an easier way, if you're worried about that, is just go with a single socket type solution, whether Intel or AMD. Any other questions, Lauren?
Oh, it looks like we just got one. It says, given the rules of thumb being stated for node sizing, e.g. 192 gigabytes RAM, 7 cores, 1:4 cache to capacity drive ratios, etc., what range of cluster storage sizes and workloads are these good for?
That's a great segue to the design utility. So let me share my screen really quick, and then we can talk a little bit more about kind of what we're doing to take a lot of this this experience that's out there in the field from folks like Anthony and Paul and engineers at OSNEXUS. Let me see. Can you guys see my screen now with the design utility? Okay, great. If you go to osnexus.com/Ceph Designer, this is we're always kind of quarter by quarter adding more and more capabilities and features to the design utility. But essentially, when you're sizing things, you need to add, as Anthony was saying, you want to have somewhere around minimum of 4 gigs of RAM per OSD, per data device. and some of these other factors around increasing the CPU. And so what we've been doing is putting, if you just put in your use case, the amount of capacity you need, it'll go and change the design based off of your planned hardware config. So if you're planning on doing like a Dell configuration, like one of the R740XDs, it'll show you how many servers you need, and then you can choose the different drive sizes, and it will scale the hardware over here to show a different processor core depending on the number of drives that go into the box, depending on the capacity chosen. And here you can adjust to choose kind of like the best NVMe device or what have you, and then you get this specification over here on the right. It's good to work with a Ceph expert. OSNEXUS is happy to help you spec out your designs, and you can email sdr@osnexus.com to get assistance on that. But you can go in here and choose all these different configuration parameters. We don't yet have synthetic performance graphs that get generated by that, but that's where we're headed. We want it such that we can take a lot of the information about that we have on how Ceph scales and what kind of performance that you get, and help translate. What does this config look like in terms of total throughput and total IOPS. But encourage you to have a look at the utility. It can really help save you a lot of time in terms of designing and figuring out how to design something for a particular use case. This at the top, when you choose the use case, after you choose the capacity, you can say, I want desktop and server virtualization. It's going to change this to what we were talking about on the call today, to a replica-based layout. If you choose something that's like a cold archive or large-scale archive, it's going to choose an Erasure Coding level like 8+3. So this is really kind of changing the storage layout and some other scaling factors to help match this capacity to that use case and try to make it as efficient as possible. We have a few sliders down here where you can control, like if your data is not compressible, you just set that to 0. And this is actually a topic that I meant for us to talk about today, and maybe that we could do that as, let's see, where are we at for time? Yeah. Why don't we wrap up on a little bit on backfill? If there's no other questions, maybe Anthony, you could talk to a little bit about the backfill reserve space, because I think it's one of those really important things that people sometimes don't think about. And it's like if you choose replica 2 and you bought 2 petabytes of raw, then you got 1 petabyte usable, but you really have to account for that reserve space for the backfill. And maybe you could talk a little bit about that.
Sure. It's very traditional to always have some reserve space. Back years ago, when we were using UFS file systems, the system would just automatically reserve 10% of space, both so that the root user can clean up when it fills up, but also because as you started approaching completely full, your time to write would really start to spike and things like that. With modern file systems, that min-free has really increased down, where it's usually like only 1 or 2% by default. But I think what we're looking at here is, say you have a cluster that's in 2 racks. What happens when one of those racks fails? And it happens, I've seen it, be that networking or a power inductor and a power supply takes down, a bunch of your PDUs or something like that. And Ceph is all about strong consistency. And Ceph will try to restore redundancy, and it's going to do that in available space in the surviving parts of the cluster. There are some things you can do to kind of forestall that so you can get it back up before the thundering herd of data moves. But you always want to reserve some space to handle failures. Otherwise, Ceph won't be able to restore, and you're in a more vulnerable state. Your cluster will, if you have your cluster laid out properly, it'll keep running, but you're more vulnerable because you don't have the replication and the redundancy that you normally do because there isn't space to redo that. And so, depending on, the number of hosts you have, the number of racks, it can pay to have a little extra headroom so that, if a drive fails, if a whole node fails, if you want to be able to reserve space to be able to restore replication until such a time that you can get that hardware fixed.
Yeah, yeah. And that's where also kind of setting that policy of, right, do you want it to, you can, I forget the exact setting, but by default in QuantaStore, we set it to a level where if you turn a host off, it's not going to automatically start the herd of rebalancing across the other nodes. And we assume that node's out for maintenance, but you can set that at a rack level or a host level.
Yeah, I think it's mon down out OSD subtree limit.
Yeah,
It has a very tortuous name.
Yeah.
If you look for subtree limit, you'll find it.
Yeah.
And
Paul,
I have witnessed that, having tremendous benefit for exactly, cases where you can be able to get the node back up quickly.
Yeah, that was something funny where I think the Ceph community or the Ceph developers set it to rack by default when it should really be host, given the more common, smaller clusters. But Paul, did you want to throw anything else?
Depends on your topology.
Yeah, exactly. For a big service provider, Anthony, like where you're where you're really scaling things out across the racks, that default is the spot on, the right way. Paul, I just want to give you one more. Did you want anything that you wanted to throw in there on the failure domains or anything like that as we wrap up?
Yeah, just one quick thought. So along with kind of the philosophy of having the space for backfill,
yeah,
I think it's also sometimes worth keeping in mind that you need some additional CPU resources when other servers go down. So it's just something to be aware of, that when you have other nodes go down, your existing nodes that are still there are going to start servicing. First of all, they're going to have to deal with the overhead of Ceph rebalancing things, but also providing the normal storage needs of your existing user base.
Yeah.
That's a very good point.
Yeah, and that kind of, it's sort of like backfill on the CPU side, right? Where it's sort of like you want to leave room for when things start to go, like a bad device is being rebuilt or a node is being completely rebuilt. What Anthony was getting at earlier with the blast radius is like, if you lose a complete node and all the OSDs that are on there have to rebalance, that's kind of that thundering herd. It's like, okay, that node's gone, it's blown up, it's going to heal. It's going to all go. That's one of the cool magical, the magic of the Ceph architectures is like, we're designed to handle that. You can pull nodes out, you can add nodes in dynamically, but you gotta give a little bit more in terms of some horsepower on that CPU, a little bit more RAM, and kind of design these clusters with a little bit of wiggle room, a little elbow room across the different parameters.
Oh, RAM too. You have to plan for peak usage, which is usually under duress, as opposed to steady state. And this ties into, somebody asked a question about very dense nodes, 45, 60, 90 drives per. And those offer, they're really appealing. One of the dirty little secrets is they take so much power that you may not be able to fit more than 4 of them in a rack, and your racks are half empty.
Yeah.
So you got to plan for that too. But then if the capacity that you need your cluster is such that you can fulfill that with 3 nodes, then if one of those nodes craters, or even if you just need to reboot it, and boom, that's 33% of your infrastructure that's down.
Yeah.
Where if you had smaller nodes, that would be a much smaller percentage. So a big part of the sizing your nodes comes down to, what's the initial footprint you're going to deploy, and having each node be, no more than a certain percentage of it. So I like to deploy clusters that have no fewer than 12 nodes, maybe 9 in a pinch, regardless of how big they happen to be, just because of the blast radius factor.
Yeah, because if
So that they're
you ever have
maintainable.
to completely swap out a node and you're looking at it as like a field replaceable part, if you lose a 12th, you know, it's not as big as like if you lose a third, like you're saying. Yeah.
And that goes, you know, into the backfill space, you know, the capacity as well, because the survivors have to serve that much more workload.
Yeah. Yep. Yeah, and that's where, you know, Ceph's real sweet spot is when, in my view, is like when you're north of a petabyte, where you really got a need for a larger config, or even, you know, north of half a petabyte. Basically, in most cases, you're going to be putting a fairly sizable investment into 7, 9, 10, 12 servers or more. It's really designed for these really large scale configurations, and to kind of keep that in mind. There's other, we do scale up configurations for the smaller type configs because it's more cost efficient to do like a 2-node with a JBOD attached or JBOF if it's something like a particular use case that needs small. But when you're thinking about Ceph, target it for your big archive or your big multi-node block storage pool, you know, like a service provider type use case, and think about it that way. That's what the sweet spot for the architecture is at. I think we're a little over time. Anthony, Paul, thank you guys so much for coming today and being on the panel. This has been just a ton of fun, and I think we hit on so many of like the different Ceph questions that we hear all the time, and I think it's just going to be a great contribution to the Ceph community as a whole. So thank you both for being here today. We're going to go have this posted online after the event. So for those that the attendees here today, look for that.